All right, so this is lecture 14 of the Real-Time Digital Signal Processing Laboratory at the University of Texas at Austin for the spring 2014 semester. And this is lecture 14, part 3. So in part 1 and 2, talked about a few things on pulse amplitude modulation, talked about transmitting one bit at a time. We had a lengthy derivation of the match filter. We'll review the practical side of that outcome today in part 3. And we'll also analyze communication performance in terms of bit error probability as a function of signal-to-noise ratio for 2PAM. For part 4, we'll do symbol error probability, eye diagram, and as time permits, intersymbol interference in more detail. We left off with slide 14, which was the result of the lengthy derivation to get the match filter formula. So just to repeat that here at the top of lecture slide 14-15. So if I know the pulse shape, G of t, that the transmitter is using, the best choice for the impulse response of the match filter is directly related to that pulse shape. And again, this is true not just in communication systems. Anytime we're trying to detect a known pulse in noise, and I mentioned other applications of sonar, radar, and ultrasound, but there are others. Range finding, lots of applications where I send out a pulse and listen for the return. So the impulse response, the best that we can do in terms of signal-to-noise ratio at the output of the sampling block after the match filter is this formula. Okay, so our pulse shape of G is G of t. In our context, we have a symbol period or a sampling time that happens after the match filter, and the sampling period is equal to the symbol time. So just to explain the terms in this formula, and then we have a gain that's very flexible. Any real valued gain will work here to maximize SNR, at least in theory. Now in practice, a gain of 0 means that our impulse response is 0 and nothing gets through the filter, not very practical. But it does satisfy, the derivation of the best match filter that we can do. So again, this is our impulse response to the match filter. That impulse response is a scaled, conjugated, and time reversed, and shifted version of G of t. And if you remember, the derivation was all in terms of power spectrum. And in power spectrum, we have, in terms of frequency content or power spectrum content, I suppose. For power spectrum content, we don't use the phase. The phase is gone, if you remember in our derivation. And phase shifts don't change the outcome of this formula. So here I have a delay that I show here of capital T. So this is a delay by capital T seconds. But really, any delay is fine. Right? And so we want to pick the delay that makes this impulse response causal. So if my pulse shape is, 4 symbol periods long, so if G of t were, let's see, a truncated sync, say we're a truncated sync that is 4 symbol periods long and 0, otherwise. And if I apply the match filter formula, right, so to get this is now my pulse shape. This is the pulse shape. To get the impulse response to the match filter, I want to flip this in time and delay it by only 1 symbol time. Well, that won't be causal. Right? So in practice, we want to make the impulse response causal, so we will delay it enough to make it causal. So if we look at what happens when we flip this, so the optimal formula here means that we flip the pulse shape for G of t, which is the minus t in the formula, and then we delay it by capital T. So I'm going to get something like this, which is now not causal. Right. So in practice, what we're really going to do is delay this another, 3 symbol periods. As to say, shift the impulse response of the match filter to the right so that we really want to shift this to the right. So that it's causal. It doesn't affect the optimality at all, because again, we don't care. A delay in time means a phase shift. And all the derivation that we did depends on the power spectrum where phase is gone. Phase is not part of that derivation. So any delay is fine. It works just fine. Now, so the duration and the shape of the pulse shape is now determined completely. Sorry, the duration and shape of the match filter impulse response is completely determined by the pulse shape. And if you look at this in terms of frequency response, the frequency response of the pulse shape is going to be the frequency response of the match filter will be the same as the magnitude response of the match filter will be the same as the magnitude response of the pulse shape. That's it. It's that simple. Now the phase is going to be different a little bit because we've delayed it a little differently and so forth, but it's still a linear phase. But if we delay by a constant, we just change the phase by a linear factor. So we're not distorting the phase other than linear phase, which is very easy to undo. But the magnitude response will be the same in the match filter and in the pulse shaping filter. So if the pulse shaping filter is low pass, the match filter is low pass. And that's what our pulse shapes have been. They've been low pass. All right. So that's one side of this formula. Now, in the derivation, we came up with the maximum. So this pulse shape, this match filter impulse response, H opt of t, maximizes the signal-to-noise ratio at the output of the sampling block. And the question is, well, what SNR is that? How high can that go? How big can it be? And in the derivation, we came up with that bound. Okay, and this bound was the maximum value that this nu could take, which was a measure of peak pulse SNR. And if you look, and that came up a couple of slides ago, and if you look at what it looks like, if you isolate the two terms, I've got this term, which is what? What is that term, if you remember? It's related to the variance. It is. The variance was n naught over 2, right? So you're on the right track. So the variance that we set up earlier was this n naught over 2, and so 2 over n naught is just 1 over the variance. And that kind of makes sense that we've got noise power is in the denominator. And the signal power was in the numerator, right? So signal-to-noise ratio measure. So the signal power is the second term in this product. Okay, and there's the term that corresponds to something about power, signal power. Okay, now this is actually signal energy, which is interesting. If you look at it, we're integrating the power spectrum overall frequency. So we're really finding the energy in the pulse shape. And you can compute that energy in the pulse shape either in the Fourier domain or in the time domain using Parseval's relationship or theorem. And so which domain you pick is whichever is easier to work with. So if the pulse shape is a rectangular pulse in the time domain, which domain would you go with? Time. Much easier. If the pulse shape were a two-sided sink in the time domain, go to the frequency. Or if it's raised cosine, go to the frequency. It's easier. Right? Right. So you get to pick which domain to go with, to go after, the answer. So this SNR, in the end, this is an extremely important result. This is the energy per bit, which means energy in the pulse shape, divided by the noise power. That is a signal-to-noise ratio measure. Okay, and we call it SNR. The old name for this, there's an old name that I don't hear anymore, but back in the 90s, we would have called this EBNO for that term, and no one would ever know what you're talking about unless you're really into the field. So I haven't heard that in a long time. So we just call it SNR. That's something that a wide audience of engineers at least would understand. Now this is important because in a communication system, we have certain SNR operating points. So based on the channel conditions, we are going to operate over some range of SNR. And so if we want to test the system that we've designed, the transmitter and receiver, we have to pick a range of SNR values over which to test our design, simulate in MATLAB to start with. And so different systems have different SNRs. I'll just give you a couple. So in wireless scenarios, in mobile cellular, it's in the -3 dB to say, 20 dB, well, -5 dB to say 15 dB range. Could go to 20, depends how close you are to the base stations or a base station. For power line, we go from -5 dB to 5 dB. For DSL, we go all the way up to 60 dB. I mean, it's a much nicer environment in DSL. It's nice shielded. It's at least twisted pair, which isn't shielded, but twisted pair. Cable is even better with coaxial, cabling. The SNRs are also in the 60 dB range. So there's so it just depends on kind of, what system you want to simulate as to what SNR values are relevant to your simulation. And so in simulation, what we're going to do is keep the signal power constant and change the variance of the noise that we synthesize in the channel. That allows us to test the system over different SNR points. So if I know what the energy per bit is, and I know what the variance is, it tells me what the SNR is here, and this is in linear units, not in dB. We have to convert to dB. So this maximum SNR value does not depend on the pulse shape, which is interesting. It only depends on the energy in the pulse shape. So you can reach this bound with all kinds of pulse shapes. Pick your favorite one. As long as the match filter is chosen as above to match the pulse shape being used. This maximum SNR is proportional to the signal energy and inversely proportional to the power spectral density of the noise, the additive noise in the channel. And again, this power spectral density of the noise is a model of the actual noise. It's not the actual noise. Go ahead.
What makes some pulse shapes more desirable than others?
So what makes some pulse shapes more desirable than others? Well, it's the usual thing, signal quality, versus implementation complexity trade-off. So a wider pulse shape is better. A longer pulse shape is better, but then I have more complexity on the other end, on the receiver side to deal with. Because ultimately this match filter is an FIR filter. The longer that filter is, the more multiply accumulates I need, and if I do this in discrete time. Let's see what else is. Simplicity. So rectangular pulses are really easy to work with. I don't have to worry about multiplication. I just add. All right. But they're short. Right? Rectangular pulses are only as long as the symbol time. So there's a trade. So it's a very short pulse relative to, say, a raised cosine that's 6 or 8 symbol periods wide or long. Now the communication standards will specify the pulse shape being used. So there really isn't a whole lot of choice on the implementation if you're going with the standard. But if you have your own system, which many cases do, proprietary system, or you're looking at the next generation of something, then you would have the freedom to choose different pulse shapes. A standard may also let you pick from among, say, a set of them. Say, here's our 6 possible pulse shapes you could use, and the receiver and transmitter have to negotiate, which pulse shape to use at the initial connection time. That also can happen. Basically longer, and the reason longer is better, though, or wider, a longer pulse shape is better, is I get a longer look at that on the receiver side. Okay. Now another property with pulse shapes that is very nice is that they have 0 crossings at integer multiples of the sampling of the symbol time. So that's another kind of thing we like to have with our pulse shapes. Raised cosine has this, sync has this. Rectangular pulse has this because it doesn't have anything beyond one symbol period. Right. So there are a few other properties we like to have of the pulse shape that we're using. Go ahead. Oh, because we're doing, so far we're doing everything with 2 PAM. You can generalize this, and we will. Next, in part 4, we'll talk about energy per symbol. It's coming. Okay, now let's look at an application, another way to do match filtering. And this goes back to when I asked you, what's the best way to detect what bit had been transmitted, given that the channel had additive noise? And you said average over the symbol time, and then compare that against the threshold. And I told you that's the best thing you could do, and here's why. So here's the rest of the story, the quantitative side of that story. So here's an example of match filter for a rectangular pulse shape. Again, the transmitter will use a rectangular pulse for its pulse shape. The match filter will also be a causal rectangular pulse shape. And we looked at this earlier. If my pulse shape is a rectangular pulse of duration t sim, this is g of t, then the best choice for the pulse shape is I flip this pulse shape along the time axis, delay it by 1 symbol time, and I'm back to where I started. Except that I have a flexibility of a gain. So that's the best match filter. That is the best choice for the match filter impulse response, is another rectangular pulse. Same duration, but now the gain can be anything, not just 1. All right, so let's look at what, there's a nice implementation for this in continuous time analog circuitry that makes this detection really simple to implement. And yeah, and we'll show that it's the same, you get the same result as using a match filter as an FIR filter. So let's go through that. Okay. So normally we would have in our receiver the match filter. Right, so normally this would be the match filter followed by a sampling operation at the symbol time. That is to say, we'll do something over 1 symbol period. We'll take the last result, or we'll take the result at the end of that symbol period, and then we'll compare it against 0 if it's 2 PAM. And we're going to do this at the end of every symbol period to figure out, or at least estimate, what bit pattern or bit have been transmitted. So normally this match filter would be a rectangular pulse. And so if you look at what happens if I convolve a rectangular pulse and with itself, so if I convolve g of t with h of t, which would happen if the rectangular pulse was the impulse response for, or were the impulse response for the match filter, then what's the result of convolving the 2 rectangular pulses? Triangle. And how wide is that triangle? Twice as long, and is it causal or not? Yes, I'm convolving 2 causal signals, g of t and h opt of t. So let me fix that one. So this is g of t convolved with h opt of t. I get a triangular result. The maximum value occurs at the symbol time. That's a good thing. We want to get as much signal power through as possible, and we do that. And what's the amplitude here at t-sim? K times K times TS. So it's basically this peak value occurs when I have maximum overlap between the 2 rectangular pulses when I flip and slide one of them about the other. So eventually they line up nicely, exactly, and I get the maximum value, which is just the area under the product, right, of the 2 rectangles. The maximum area possible is when we have complete overlap. So base times height, right? So T sim times K. That's it. Now the good news, now the rest of the story in the match filter is after the match filter, I sample at the symbol time. So the match filter, I'm going to do the match filter, and then I'm going to sample at the symbol time. So I'm going to sample right at this peak value, which is great. That means that's where I have the strongest signal power. Excellent. Okay, so that's the standard way of doing the match filter. Now I can get an equivalent implementation using a different set of processing blocks, and that is that I can do what you said earlier, which is integrate over one symbol time, and then take the result and compare it against a threshold or thresholds. So if it's 2pan, we compare against 0 to decide what bit had been transmitted, or estimate which bit had been transmitted. So this integrate operation works very nicely. So now, the question. I actually promised this earlier in the semester. What is the impulse response of the integrator? It's the unit step. That was excellent. It's rare it comes back that fast when I ask this semester to semester. Again, all it means is the impulse response, right? What's the definition of the impulse response? I put the impulse as the input, and I look at what comes out at the output. I put the impulse, the direct delta, in to an integrator. What comes out is the step. Right? That's the relationship between the two. So the impulse response is U of t. Doesn't look like we're always quite there yet, but now think about a pulse shape that's coming down. Let's ignore noise for a minute. So here's a pulse shape that comes down. All right, comes to the receiver. And what's the convolution of a rectangular pulse and a step? What does that look like? Yeah, there's a triangle and it becomes a rectangle. Another way to say it is that there's a ramp and then it is constant. Lots of ways to describe this. There's a ramp and then it becomes constant. No, because the step is from 0 to infinity, right? Has value 1 from 0 to infinity. So this rectangular pulse, we flip and slide the rectangular pulse, we get partial overlap and then complete overlap with the step. Now what's this value? What's the value that it takes after the ramp? What's the maximum value? What's the maximum value, where the question mark is, after the T-sim? Yes, that's correct. In other words, it's the area when I have maximum overlap between the rectangular pulse and the step function. I multiply the two together, and the maximum overlap would be when the rectangular pulse is completely inside the step as it slides left to right. And so I end up with T-sim here. So the answers are very similar from the top of the slide to this part of the slide, except that the answer up here depends on, has the dependency on K, but I can just let K be 1, and it works just fine. Go ahead.
So on the top one, is that assuming K is less than 1?
The top one assumes that K is any real number. So the K here is any real number. Now, 0 is theoretically okay, but it's not practical. So we do exclude 0 in practice here. But any K can be negative. What it allows us to, the flexibility of letting K be a constant that the receiver can set, is it lets the receiver do automatic gain control. So the receiver can adjust the gain at its input, and this still works. This optimality is retained, even in the presence of automatic gain control, which we'll need in practice because signals fade in and out, and noise comes and goes, whatever. So there are reasons that we want to adjust the gain at the receiver. This allows us to do that. This result allows us to do that. Okay, so let's look at the... All right, I didn't say where this peak occurs. The peak occurs initially at at tsim. Okay, so that's the good news. So I get a peak at tsim just like I got a peak at the symbol time in the above approach, the standard approach. Now, the value I care about is the value at tsim because I'm sampling at tsim. So that's the one I want, and I really want the peak value to be there. It's okay if there's another peak somewhere else. I don't really care. I really want a peak at symbol time. All right, so what does implementation really entail? I integrate the received signal for some amount of time, and then I sample the value at the end of that amount of time. It's usually slightly less than the symbol time because I have to leave room for the discharge. So I charge a capacitor, take the value by sampling, and then I discharge the capacitor. So this discharge response of the capacitor, and again, it's going to have a different resistor attached to that, so it'll be a different time constant. But we really want a very fast discharge time and a slower charging time. So the RC constants will be, the RC time constants will be different. So again, a charge, discharge, discharge. And it's a very simple receiver, very simple matched filter implementation. It's just an integrator followed by a sampler. So sampling can be done with one transistor. So it's pretty simple implementation. Okay, but they're equivalent. Now for us in lab, we're going to be in discrete time, and so we're going to go with the upper approach, and we'll make the matched filter a discrete time FIR filter for use lab 3 and other experiences in the class. Now you can also see that we'll see this as we now move to slide 21. Any questions on this before I move on? Good. So you asked about why you choose certain pulse shapes. So rectangular pulse, just everything is just so much simpler in terms of complexity in both the analog continuous time domain and a digital discrete time domain. But it's limited. It's not a very long pulse shape. Let's move to slide 21. Okay, I have a handout to give you on Friday that will have a little bit more details on a couple of these claims, but I'll go through, and I have a derivation of the claim in particular here in the next slide. All right, so we're going to do bit error probability for 2 PAM. And since it's 1 bit per symbol, 2-level PAM, our bit period is the same as the symbol period. They're going to be synonymous. All right, so T sub B is our bit period. The bit rate is 1 over the bit period since it's only 1 bit per symbol, or one. There's 1 bit in the bit period, and therefore the bit rate is the inverse of the bit period. The operations here are very similar to what we had before. Again, I have a transmitted signal, which will be my pulse-shaped transmission to PAM, and that's shown over here on the right. Just interpolation. AK here is the symbol. AK are the symbol amplitudes. And for us, since it's 2 PAM, this will be either D or minus D. Or in our case, it's either going to be A or minus A, either capital A or minus capital A. It's 2 PAM. The received signal is going to be just the sum of the transmitted signal and the noise. That noise, again, is spectrally flat. The amplitude of this noise signal WT is spectrally flat, follows a Gaussian distribution, has 0 mean, and variance sigma squared. The output of the matched filter is simply the convolution. So the output is R underscore of T. This is just a convolution of the impulse response of the matched filter and the received signal. Now, a couple of things that are from the handout I'll give you on Friday, but and I mentioned I derived the second one on the next slide. One of the reasons to work with Gaussian random processes is they really work nicely with filters. So if we apply a low-pass filter to a Gaussian random process, again, WT is an example of a Gaussian random process. Right? For us, a random process, simply defined, means a random signal whose amplitude follows a distribution, a specific distribution. So if I low-pass filter a Gaussian random process, for example, W of t, this will produce another Gaussian random process. How cool is that? Don't have to worry about changing distributions. But the parameters of the distribution change. For a Gaussian distribution, we have two parameters. We have the mean, we have the variance. So the mean is scaled by the, remember the mean means the DC value, the average value, the zero frequency value, if you will. That mean is scaled by the frequency response of the low-pass filter at DC. So if the mean is already 0 on the input signal to this low-pass filter, then the mean remains 0 on the output. Go ahead.
Gaussian random process. About that. That could be null. That's the signal being represented in the frequency domain, right? So
No, it's the amplitude domain. So we're saying the amplitude statistics of W of t. So for any value of time little t, the amplitude is a random number from the Gaussian distribution. And that Gaussian distribution has zero, in our case, has zero mean.
So
and
it's more like this Gaussian distribution kind of exists for all time steps.
Correct. So for all, and the Fourier transform of this signal does not exist.
Okay. Yeah.
That's the problem. But the power spectrum does. So the power spectrum, if we were to observe W of t for all time from minus infinity to infinity, this is theory, then the power spectrum is flat and the value is sigma squared. All right, so the mean, the filter, the slow-pass filter will scale the mean by its DC response. And the variance will be scaled by twice the low-pass filter's bandwidth. Okay, so that's interesting. So we're actually going to get, this low-pass filter will now shape the spectrum of the Gaussian, of this Gaussian random process, right? The power spectrum is flat, but after it goes through a low-pass filter, that power spectrum will now be low-pass because we filtered out, in principle, higher frequencies. Now, if you sit back and think about the match filter actually has a lot of roles to play. There are actually 3 of them. It's a versatile filter. So the first role of the match filter is to maximize the SNR at the output of the sampling block. That was part 2's derivation. But there's another role from a signal processing perspective. And what role do you see here in the block diagram? That should look really, really familiar. Filter plus the sampling. So what's the role of the match filter? It's a low-pass filter. Well, we're still in continuous time. We're about to sample. Right? All this is in continuous time, and then we're about to sample, right? So what's that low-pass filter doing before the sampler? The sampling will replicate the frequencies. It's attenuating. We'll stay on one particular bandwidth. Still looking for the right phrase, but the descriptions are correct. This is the anti-aliasing filter for the sampling operation. So its job, if the sampling rate's at T sub b, then what is the stop band frequency of the anti-aliasing filter? So I'm sampling at rate FB if you want. So however you want to phrase it. Half FB, right? So it's an anti-aliasing filter to control the amount of aliasing. Now, in theory, I suppose we can say we eliminate it, but in practice, right, we're going to design the match. So we designed the match filter to control the amount of aliasing that happens. Go ahead.
Why wouldn't you want to sample at twice the bit rate?
Oh, you can oversample. That's a whole different. We'll get it. That's what we do in discrete time. We oversample, and you can do this in continuous time. We could sample at 2 FB if we wanted to. This is an oversampled case, which is our normal case in discrete time, right? Because in discrete time, the sampling rate was an integer multiple of the symbol time. The sampling rate was an integer multiple of the symbol rate. So in discrete time, we're going to have capital L samples per symbol. We are going to oversample. Well, so the stop band here, so this match filter, you can argue you can talk about cutoff frequencies, which I do in the last bullet. So the match filter is the anti-aliasing filter. So the match filter maximizes SNR. That's sampling output. And it's the anti-aliasing filter. So the way that we define it here is that the cutoff frequency, which is that value in between it's in the transition band, maybe half the amplitude in linear units is, or the 3 dB point if it's power, 6 dB point if it's amplitude, below passband is half the symbol rate, or half the bit rate. Now from a signal processing perspective, we tend to put the stop band frequency at half the sampling rate. And the sampling rate here is the bit rate. So the way that we're going to do it here is that some measure of bandwidth is half FB. You can pick your favorite measure, whether it's the stop band frequency or the cutoff frequency. We tend to go with cutoff frequency here. But some measure of bandwidth is half the sampling rate. Okay, so we have two roles to play. Now, this is all baseband PAM. If we had bandpass PAM, upconverted PAM, the match filter would have a third role to play, which is anyway, DC components, if it were upconverted PAM. One more role to play. Let's get the right name of that role. Yes, but let's name it. Low pass, whenever I demodulate, I need to modulate followed by a low-pass filter. So the match filter becomes a demodulating filter. So you have one filter playing three roles. Why have three different filters when, three different low-pass filters in cascade is kind of silly.
Are you talking about like moving the bandpass down?
Yeah, the conversion from bandpass to baseband through down conversion. The match filter would be the demodulating filter in that case. That's three roles to play. Same one filter doing three different tasks. Okay, this is a derivation which I'm not going to go over, but I will give you the result of this. And so the result here is that this is just showing that if I have a Gaussian random process as an input to a low-pass filter, that the change in the variance is scaled by 1 over the symbol time, which is equivalent to scaling it by the symbol rate. This is equivalent to, so this is really, T is T, capital T is actually the symbol time, and so this is equal to sigma squared times F sim. This matches the claim on the previous slide that the variance is scaled by twice the bandwidth of the low-pass filter, and the bandwidth was half the symbol rate. 2 times half the symbol rate is the symbol rate. This will come into play later in our derivations of symbol error rate in part 4. All right, so let's go ahead and derive the probability of a mistake in the receiver in the presence of additive spectrally flat noise and no other impairments. So it's 2 PAM, so our symbol amplitudes will be plus A, plus capital A and minus capital A, 2 possible values. To make it simple, we'll use a rectangular pulse shape, amplitude 1. The bit duration is 1 second. We're just normalizing all the parameters to make it easy. So the bit duration is 1. We'll come back and generalize this in part 4. And we'll do match filtering with a gain of 1. So this normalized everything. Right? Everything is possible. Now we're going to use the integrate and dump circuit from earlier discussion, right? From today. So what I'm going to do is I'm going to integrate. So to try to figure out or estimate the bit that was sent at the nth bit period, I'm going to integrate over that nth bit period. Now remember, the symbol time is 1. So I'm really integrating from ntsim, or TB. This is really ntb over n plus 1 TB, but in this case, TB is 1. So that goes away. So that, and if I look at what happens, what is R of t? Well, R of t is going to be, I'm integrating R of t over the symbol time, over 1 bit period. And what's R of t? What's the received signal? What's R of t? It's a transmitted waveform, which is really just a pulse shape, plus noise. That's what we receive. Right? The only impairment is additive noise that's spectrally flat. And S of t is either going to be a rectangular pulse scaled by capital A, or it's going to be a rectangular pulse scaled by minus capital A. So you send a bit of value 1 would be the one on the left, bit of value 0 is on the right. You can do the other way around as long as the receiver knows. So if I integrate S of t, remember the symbol time is the bit, so again, just to correct this, so this is all the, well, symbol time is the bit time. All right, in this example. One second. So if I integrate over 1 second this rectangular pulse, it's 1 second in duration, then the area would be simply A. Right, so the area here is A time, base times height 1 times A, so I get A. So either get plus A or minus A, depending on which bit I had transmitted. Then what's left is integrating over the bit duration the noise. And this is nothing but a low-pass filter. And it works well because we only integrate for a finite amount of time. We don't have to worry about unboundedness for a DC input for all time because we're going to reset the integrator every symbol or every bit duration and discharge the memory to 0, or set the memory to 0 by discharging capacitors, or the capacitor, sorry. So I end up with the result of this low-pass filter applied to the noise, and I take the value resulting from integrating over the symbol, over the bit duration, which is one number. It's a random variable, v sub n. Go ahead.
Since normally when we use these kind of systems, we're going to have noise, and we always we're going to estimate. So even with noise, we'll always choose whether it's negative A or A. How does this tell us the chances of making an error if we're always making binary choices? Like, because that's where the noise.
Yeah, well, we're getting there. So that should happen before the slides are out today. So it's good there. Yeah, so it's going to be related. The bottom line is the probability of making a mistake. So the probability of getting it correct is the higher the SNR, the more likely I get it correct. Okay, so if I look at what happened, I have now a random variable. This is a random variable, R of n. It's equal to a constant, to the plus A if it's bit of value 1 minus A bit of value 0, plus another random variable. So the random variable V of n is Gaussian from earlier discussion, and the random variable R of n is still a Gaussian, but the mean value has been shifted because I'm adding either constant of plus A or minus A. So if I send a bit of value 1, so send a bit of value 1, this is the distribution. It's Gaussian with the mean at capital A. If I send a bit of value 0, my Gaussian distribution is now centered at minus capital A. And I have to figure out, what's the likelihood of either one, and we just assume they're equally likely. So we're equally likely to send a bit of value 0 or a bit of value 1. Okay, and remember, we're going to integrate in threshold against 0 because we're assuming equally likely transmission of 0 or 1. All right, so let's go through the probability of making a mistake. So the probability of error, given that we transmitted an amplitude of minus capital A, is the following. So the probability of error, given that we transmitted an amplitude of minus capital A, which for us is a bit of value 0, for just my current choice, then what that really means is that I want to know when the PDF, which is now a Gaussian probability density function centered with a mean of minus capital A, when is that giving me a positive value? Because if I threshold against 0 and I send a bit of value 0, I'm going to make a mistake. Right? So I'm correct if this term, minus A plus Vn, is negative, I'm good. So I threshold against 0, I get a negative value, I choose the right bit. However, it's positive, it means I made a mistake. So I can just add A to both sides, capital A to both sides, and divide by sigma because sigma is a positive number. It's not negative, and it's not 0. And so now I'm comparing a random variable that's been scaled by 1 over sigma. So what happens to its variance from homework 4? I'm scaling remember, V of n is just a random variable. Gaussian distribution. What happens to its variance? Scaled by 1 over sigma. That's right. So the variance is scaled by 1 over, is divided by sigma squared, or scaled by 1 over sigma squared. So it turns out the variance of V of n is sigma squared. So this becomes a unit variance from what we learned in homework problem 4.1. V of n is still has a mean of 0. That hasn't changed. And the variance now is 1. Okay, so when this inequality holds, basically what I need to do, what's the probability that this normalized V of n over sigma is greater than A over sigma? Well, it's this part of the PDF. It's in the tail. So if I integrate the area under the tail of this normalized random variable, Vn over sigma, then that's the probability of making a mistake. Okay. Hard to do this in closed form, so we integrate the probability density function from A over sigma to infinity, which is the tail. And we have a placeholder expression here called the Markham Q function. I'll plot that on the next slide. And if you look at what's inside the argument, you'll see something in the numerator that looks like the signal. Right? A is the amplitude of the signal, or minus A. Something to do with the amplitude of the signal at the transmitter side. And what's in the denominator is something that looks like something about the noise. Sigma. Right? The noise power is sigma squared. So let's go to the Q function to see what happens. So the Markham Q function you can obtain from built-in functions either in MATLAB or Mathematica. So if it isn't built in, you can estimate it using either. So you can just define it in terms of the complementary error function. And that's built into MATLAB and Mathematica. So this Q function, as x increases, the Q function drops dramatically in value. So you'll see that so again, as x increases, and x is related to the SNR in our case, so it's actually the square root of the SNR, and I'll show you that in a second. But as the SNR increases, then the probability of making a mistake dramatically decreases. And it's a dramatic reduction. And if you look at its behavior down here, it looks a lot like a decaying exponential. So you get a tremendous reduction. For a little bit of improvement in SNR, you get a tremendous reduction in the probability of making a bit error. It's huge. It's amazing. Exponential. Okay, it's going to wrap things up with this slide, so just hang on. So the probability of the other case, which is I send an amplitude of capital A, and I make a mistake. So if I threshold against 0, I'm expecting a positive answer, a positive number. But if I get a negative number, I've made a mistake, and it turns out it's the same probability of making a mistake. It's the tail, but the negative tail in that normalized distribution. So now if I kind of put those results together, probability of error is the probability of sending amplitude A times the probability that I send a value of the amplitude of capital A, plus the probability of sending an amplitude of minus capital A times the probability of error given that I sent an amplitude of minus capital A. So if I assume equally likely and send in a bit of value 0 or 1, then I get 1/2 times the probability of error, which is the Q function for the first case, and 1/2 times the Q function for the second case. Add that together, and I get a very simple relationship. I get the Q function, the total probability of error is the Q function of A over sigma, and it turns out this A over sigma is exactly the square root of SNR, or an SNR measure, given all of our normalized parameters. So we have SNR is going to be equal to signal power divided by noise power. And there's also and this is a bound that just kind of shows what this Markov Q function looks like as a function of square root of SNR. It is an exponential decay with a scaling factor. Okay, and I think that's where so this is a very simple measure. So as SNR increases, the probability of error dramatically decreases. Because this argument is going through, this argument here of square root of SNR is going through this Q function. So again, higher the SNR, lower the probability of a bit error in the receiver. Okay, see you on Friday.